Okay, let's dive into this. Welcome to today's explainer. We are cracking open the fascinating, sometimes kind of intimidating, but absolutely rewarding world of 3D kinematics. If you've ever watched a robotic arm flawlessly build a car, perform microscopic surgery, or, even just sort packages at a warehouse, you've witnessed exactly what we're going to decode today. We're going to take a raw piece of engineering source material, a pretty complex robotic manipulator problem, and translate its dense wall of math into clear, visual mechanics right here on your screen.
Here is our roadmap for this explainer. First, we'll define the robotic arm problem. Then we'll break it down into the motion of the base, followed by the moving reference frame. And finally, we'll combine those two to calculate the total velocity and the total acceleration. We'll conquer this one logical step at a time.
All right, part 1, the robotic arm problem. Let's start building our bridge from the physical to the mathematical.
Okay, I want you to do me a favor and completely ignore all those daunting equations at the bottom for just a second. Let's anchor ourselves in the actual physical geometry we're looking at. We've got a robotic manipulator moving in 3 dimensions simultaneously. That blue base, it's spinning, and the brown arm attached to it is pitching up and down. Let's check out the dimensions. The arm's base connects right at joint B, pitched at an angle phi of 30 degrees. The arm itself stretches out to a length r of 1.6 meters and is angled at theta equals 45 degrees. This specific geometry, right here, is literally the foundation for everything we're about to do.
So, what does this all mean? Well, all of those dimensions, all of those moving joints, lead us to one single ultimate goal. At the exact instant shown in the diagram, what are the velocity and acceleration of grip A? Grip A is the business end of the robot, right? It's the part holding the laser, the wrench, the scalpel, whatever it is. If we don't know exactly how fast it's moving and how quickly it's changing speed in 3D space, well, the robot is useless. Finding grip A's motion is the whole shebang.
To conquer this, we absolutely need a clear attack plan. If we try to solve for grip A all at once, the math just becomes a chaotic mess. Instead, we'll use a simple 3-part strategy. Step 1, we isolate the base and find the motion of joint B. Step 2, we imagine we're actually riding on that moving base, and we find the relative motion of grip A from that perspective. Step 3, we use the magic of relative kinematics to stitch those two realities together. See, no reason to panic, just 3 steps.
Moving right along to the first phase of our plan. Part 2, motion of the base.
Let's isolate the movement of the base and joint B. So let's freeze the rest of the arm and just look at the bottom piece. First things first, we need to know exactly where joint B is in 3D space. We're going to call this the base vector, RB. Looking at the geometry, the support structure is 1.2 meters long and it's tilted off the vertical z-axis by that phi angle of 30 degrees. Using some basic trigonometry, we find its projection along the y-axis, which we denote with the letter J, and the z-axis, which we denote with K. That gives us a really precise coordinate, 0.6J plus 1.0392K.
Now let's make it move. The setup tells us the entire base is rotating around the vertical z-axis at an angular velocity of 5 radians per second. Because it's around the z-axis, we're going to write this as 5K. To find the linear velocity of joint B, which we'll call VB, we take the cross product of that angular rotation and our position vector. When we cross 5K with our RB vector, the math tells us joint B is moving at -3 meters per second along the x-axis, represented by the I vector.
So, the base is moving, but is it accelerating? Actually, yes. Even though the base spins at a constant 5 radians per second, the direction of joint B is constantly curving into a circle, meaning it is for sure accelerating toward the center. We calculate this base acceleration AB by crossing the angular velocity with the linear velocity we just found. 5K crossed with -3I results in -15J meters per second squared. That J tells us this physical acceleration is pulling squarely along the y-axis.
Great, step 1 is complete. Let's look at part 3, the moving reference frame. Now we are going to pretend we are standing right on joint B, spinning right along with the base to calculate the arm's separate motion. This perfectly illustrates the heart of 3D relative kinematics. We literally have 2 entirely different rotations happening at once. The base rotation, omega-1, is spinning at 5 radians per second around the fixed vertical z-axis. That's our big capital omega 5K. But the arm rotation, omega-2, is lifting up and down at 2 radians per second around a local x-axis that is turning with the base. We call this local rotation omega xyz, and it's equal to 2I.
We absolutely must keep these completely distinct.
So imagine standing on joint B looking up at grip A. What do we see? Well, the arm is 1.6 meters long, angling down at 45 degrees. Just like we did for the base, we use trig to map this position. This is RA/B, the position of A relative to B. The calculation gives us roughly 1.1314 J and a negative 1.1314 K, since it's pointing downward relative to that joint.
So how fast is grip A moving from our spinning perspective? We take that local arm rotation we just talked about, the 2I, and cross it with a relative position vector. This cross product yields the relative velocity. The math crunches down to 2.2627 J plus 2.2627 K meters per second. This is exactly how fast the robot's arm appears to be moving if you were bolted to its spinning shoulder.
We finish off the moving frame by finding the relative acceleration. Just like before, the arm is rotating, so it's constantly pulling grip A in an arc. We cross the local rotation, 2I, with the relative velocity we just found. This gives us our final puzzle piece for step 2, a relative acceleration of roughly negative 4.5 J plus 4.5 K meters per second squared. Awesome. We now have all the raw materials we need.
Now, what's really interesting about this next slide is how it all comes together. Part 4, calculating total velocity.
This is where we finally get to pull the curtain back and see the big picture. We are combining the two halves of our reality. To do this, we use the relative kinematics equations. Look, I know equations can look like a foreign language, but conceptually, this is really just a master formula. It states that the true velocity of grip A is simply the velocity of its base, plus the velocity caused by the base's rotation swinging the arm around, plus the relative velocity of the arm moving on its own. It's literally just adding our puzzle pieces together. Honestly, it is so satisfying to watch this assemble. We take V, we drop in our base velocity, negative 3I, we drop in our base rotation, 5K, and cross it with our relative position. Finally, we add that relative velocity we found in the moving frame, the 2.26's in the J and K directions. Every single one of these numbers is something we've already calculated and understood. No surprises here.
And boom! When you run that final bit of cross-product arithmetic and combine your I's, J's, and K's, you arrive at the ultimate 3D velocity vector for grip A. It is moving at negative 8.66I plus 2.26J plus 2.26K meters per second. That right there is absolute precision. The engineers now know exactly how fast that grip is slicing through the air in all 3 dimensions at this exact millisecond.
All right, home stretch, part 5, calculating total acceleration.
Knowing the speed is great, but it isn't enough. We need to know the force, the change in speed. That brings us to the mathematical climax of our explainer. I'll admit, this equation looks absolutely terrifying at first glance. It is a massive multivariable beast. But remember our strategy. We already have AB. We already know omega and RA/B. We already found our relative velocity and relative acceleration. This master equation is just the final assembly line. Nothing here is an unknown.
So the crucial trick here is just methodically dropping the raw numbers into their slots. You have the base acceleration on the left. The middle term handles the centripetal acceleration of the whole system spinning. Then there's that fascinating term with the 2 in it. That's the Coriolis acceleration. It's kind of a phantom force created by moving linearly inside a spinning frame. We add 2 times the base rotation crossed with the relative arm velocity, and finally we cap it off with the relative acceleration on the far right.
Crunch all those vectors down, carefully tracking your positive and negative signs, and there it is. The ultimate 3D acceleration vector emerges. The final acceleration of grip A is negative 22.6I minus 47.8J plus 4.53K meters per second squared. We have mathematically conquered the physical robot. We started with a picture of a mechanical arm and decoded the exact physical forces acting on its very tip.
And listen, this is definitely not just an academic exercise. This is exactly how the real world operates. These precise multi-frame kinematics equations are exactly how engineers program robots to avoid complete disaster. Think about it. If a single rounding error in that moving reference frame shifts this final vector by just 1%, does this surgical robot delicately grip its target, or does it absolutely crush it? Understanding this math isn't just about passing an engineering test, it's about controlling the physical world with absolute, uncompromising precision. Thanks for joining me on this explainer, and keep decoding the world around you.